how enthusiastic are to learn photoelectric effect? We are doing photoelectric effect today. How enthusiastic are you to learn photoelectric effect? Okay, enthusiasm level has increased. Yesterday there were 10% students who said not at all enthusiastic. Uh, so before we do photoelectric effect, how much do you know? At least do you know what that is? What is photoelectric effect? Okay, that's good. That's good. Okay. So everybody is giving the answer emitting electrons via the photons. Yeah, that is what is photoelectric effect. So let's do a quick recap of what we did yesterday and we'll go a little slow and study that one more time. So what we did yesterday was this. Let's say there's a piece of metal. So this is a summary of what we did and we'll go through the slides one more time, please. Everybody focus on the whiteboard. So there is a piece of metal here. Now, metals have free electrons. Free electrons move around. They are free birds, right? So they keep moving around. One or couple of them at times they might actually do this. They might come out briefly, and then but as soon as they do that, this becomes positively charged and pulls it back. Come back, don't run away. So basically, it's like a house. You can go out of the house, or there's a dog that can go out of the house, but he's on a leash. So he can roam around but never escape, right? So electron can briefly come here but then immediately comes back and can come here, maybe it goes back. This happens. It is happening right now here. Okay. But then, so it's like, okay, it wants to escape. It doesn't have enough energy to do that. What if I give it some energy? So we saw a couple of ways to do that. We said, what if I heat this up so that thermal energy will give it enough energy and it is going to become free, escape. So this is called thermionic emission. Okay, thermionic emission. Similarly, what you can do is you can put a field here, maybe very strong positive field, very strong positive field. So electron will be attracted to that. This is called field emission. What we are interested in is we take a photon collides with this, gives all its energy to that, and it becomes free. This is called photoelectric effect. Photo means light. So you're throwing some light, and the photons of the light they are actually making it free, right? This is what we did yesterday. Now we also did photons. So what is a photon? Can anybody tell me? Okay, maybe I'll do a poll on that. What is a photon? Yeah, more students joining in now. So whatever has been missed, please see a recording of that. Okay, so everybody is giving one and only one answer here. That is, it's a packet of energy. Okay? So we are going to start with all the slides that we covered yesterday, and we'll go a little faster. And some students were not in here, so they should pay extra attention. So dual nature of radiation and matter. I spent some time yesterday to explain all the history of Newton and then Young's double slit experiment, and then how Einstein comes into picture, and how the radiations are dual in nature. They are waves and also particles. And I also said you sitting on the chair there are also a wave and a particle, right? So if you have missed yesterday's class, I would advise that you see the recording of that. So quantum theory of light, we are quantizing the light energy. It comes in packets of energy. So either you can have one photon, two photon, a million photon, 956 photons, but you cannot ask for a partial photon. You cannot say give me 85.9 photon or not even 85.5 photon. It's not possible. So it comes in discrete amounts. This much energy or double of this or 500 times of this or a million times of this, but not a fraction of that. So quantum theory of light, right? So now the amount of energy each photon has is equal to h times the frequency, where h is the Planck's constant. Planck's constant, its value is 6.626, and I forgot it now again. See, that's what happens when yeah, 6.626. I was right. 626 times 10 to the power minus 34. Take a tiny little value, and you can see it is tiny little energy anyways. Each photon has this much tiny amount of energy, and frequency is the frequency of light that you're talking about. You're talking about red light. Which red light? Each wavelength is one color, each frequency is one color. So plug in that frequency here, and that is the energy that you're getting for one photon. Light is a collection of all these, right? Any doubts with what is photon? What is any property of the photon? Anybody has any questions? I can answer that. So energy of photon is h times the frequency, and frequency is also speed of light by wavelength. So if you know the wavelength, you can use this. So this is the amount of energy in joules. You're going to get it in joules. You can always divide it by 1.6 times 10 to power minus 19, which is the charge of electron, and you get it in electron volts. Okay, no questions, nothing. Everybody understood? No, no, no. Arvind Thakur, you have written a sentence, but technically that is not right. So let me read Arvind Thakur's statement, and that contributes. Arvind, please keep making these comments. So this is what Arvind is saying. I will paste it here. Means the light consists of particles which move in form of waves. No, it is not particles. What? So particle would be like electron, right? Electron is a particle. Proton is a particle. It is sitting here and it is a particle. Photon is not a particle. That's the reason I asked that question. Is it a particle like electron, proton? No, it's just a packet of energy. It's not a particle at all. It is a packet of energy. And this one has h times frequency, joules of energy. It's just energy, 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 energy. It's pure energy, nothing else, nothing more, nothing less. It is not a particle in the sense that it behaves as a particle. You can say that. You can say it behaves as a particle because what are the properties of particles? This is a particle. Particle doesn't, so please listen here. This is something new I'm teaching. Particle doesn't mean tiny particle. This is a particle in the sense that I can tell its location and its momentum at a given point of time. Particles have momentum and location. I can tell this watch is here, isn't it? Waves don't have a location. If this is a wave, think about it. Where is the wave? Wave is here, wave is here, wave is here, wave is here. The same wave is everywhere here, right? Waves don't have a certain location. That actually is the difference between a wave and a particle. No, no, don't talk of mass because even photons have a mass, right? So don't talk of mass. The difference here is what I'm saying is waves don't have a definite location. They have a range of location where they are always present. Particle has a fixed location. It is here but not here. Now it is here but not here. It has to be at one and only one location. So that differentiates a particle from a wave. So we will see in dual nature of matter also. So while you're sitting on the chair, you have a fixed location, but there is a kind of uncertainty of the order of 10 to the power minus 34 meters here or here. And that makes you a wave also. Okay? So the statement actually is good to understand it, but don't use it like formally. These are not particles. These are packets of energy that can behave as particle or as wave. Is it clear now, Arvind? And everybody actually. So these are packets of energy. A photon is a packet of energy that can behave as a particle or as a wave. It is not a particle. Okay. So no questions further, then we'll move. Find the energy of a photon having wavelength 5000. So energy is equal. I'm doing fast because yesterday we did this anyways. At c by lambda. Excuse me. So I just unmuted myself. Okay. So h is 6.626 times 10 to the power minus 34 times 3 times 10 to the power 8 divided by 5000 times 10 to the power minus 10 joules. Done. If you're really interested, you can divide all this by 1.6 times 10 to the power minus 19 and call this energy in electron volts. Okay. So it's done for you. You can take a screenshot and see that. Or if you want, you can divide it by a charge of electron and call this as electron volts. It's your choice. But in multiple choice questions, you don't have a choice because you have to choose one. Properties of photons. A source of radiation emits energy. Read this. Everybody read this. Photon does not exist at rest, so it has no rest mass. It doesn't make a sense of saying photon is sitting here. Photon is not, never sitting. It's always produced as traveling 3 times 10 to the power 8 meters per second in vacuum. So there is no concept like that's what I was saying. Okay, this is particle sitting here. There is no concept of photon sitting here. Light is really strange. Light is Very, very strange. Doesn't behave like anything else in the universe. And light is the only thing that can travel with 3 times 10 to power 8. Nothing else can travel with that speed. Momentum of photons. Okay. So momentum of photon is, I think I'll cover myself. So we'll summarize here. E is equal to hf. Please note this down. Note this down. It's a summary of everything. C by lambda. You can write it down. Now momentum is energy divided by the speed. Now the speed itself can be energy was hc by lambda, है ना? And we are dividing by this. So this becomes h by lambda. So momentum is h by lambda, energy is h times of frequency. You're not going to use mass times velocity. We're not going to use half mv square. Those are like for Newtonian mechanics. This is not Newtonian mechanics coming into play here. This is a completely different thingy. ठीक है. No, the force. Now, if something has a momentum, let's take a rubber ball. It has a momentum. It hits the wall there, comes back. There is a change in momentum of the ball. That change in momentum is transferred to the wall. The rate of change of momentum is given is the definition of force, right? So that Newtonian law still holds here. So if there is a photon which with h divided by lambda momentum, and then it's coming back with h divided by lambda momentum, there is a momentum transferred to the wall which is 2h by lambda. And if there are n photons going every second, this is the rate of change of momentum, and this is going to be the force which the wall experiences. But then if you plug in the values here, these are so tiny. My hand is experiencing so many photons at this point, but I don't feel any force in here. Divided by the area, I don't feel any pressure itself. ठीक है. Now nobody is responding here. I'm assuming that you're understanding it. Everybody say yes or no. Understood. Understood yes. Understood no. ठीक है. ठीक है. If understood, then it's good. Okay. So we did this question yesterday. Do it one more time, please. Just scribble and write what you're going to calculate. Don't do the final calculation. That's 30, 40 seconds. That's all, please. Just try to understand what the question is saying. ठीक है अत्री. अत्री perfect. ठीक है. बिल्कुल ठीक है. So, ठीक है, I'll give you more time here. More students are writing here. No polls for this, just work on it. That's all. Please work on this. Okay, so let's make the picture here. There's a photon that comes in, and how much is the momentum of this? This is h by lambda. Okay. Now this photon gets reflected. If it was not reflected, then the momentum change would be h by lambda, but it is going back by h by lambda. So the change in momentum is 2h by lambda. Okay. Now, what is the pressure? 100 photons fall every second. Okay, that is the force. Divided by the area, this is the pressure. That is all you have to calculate. That's all. Yeah. So, Aktari, have you understood this, please? Have you understood? Just look at this. And then you divide by the area. Sure. Effect of medium change. Medium change के लिए हमने yesterday we wrote that down. We'll write it again. Whenever you have a wave, you need two things. One is the source of the wave, and then you need a medium for the wave to travel. And there are three attributes that we study usually: frequency, wavelength, and velocity. Frequency is decided by source, and once it is decided, it is not going to be changing. Even if the medium changes, frequency doesn't change because I created a wave, I decided the frequency. Now medium is going to decide this, decided by medium. Once the medium has decided that is the velocity, it changes the medium, new medium will decide the new velocity. This adjusts according to velocity. So everybody please see this slide and let me know, not this one. No, this is the one, yeah. So everybody understands this, right? Okay. Now we covered intensity also. Please see this slide and let me know if there is any kind of confusion here. I'm going to cover that. Energy per second is the power. Now power per unit area is intensity. So this is something we covered, and we are going to do photoelectric effect more. So all these were covered yesterday. So let's move on. Uh, yeah, we did these questions yesterday. I should have deleted these. It's my mistake. I should have deleted. So let's move on to photoelectric effect from here. Yeah, so this is where we stopped, I think. This is photoelectric effect. Okay, so this is where we are going to start now. So let's start formally with the definition of what that is. When electromagnetic radiations of suitable wavelength are incident on a metallic surface, then electrons are emitted. So let's slow down here and see the behavior what we need. So this is a source of light and this is a plate, metal plate, right? So when the light falls on it, the electrons, they will take energy and they will become free. They will escape. This is called the photoelectric effect. So electrons come out only if certain conditions are met, and that is the purpose of this whole study today. What are the conditions? It's not like why is electron not coming out of this metal? This is metal, this is aluminum. So why is it not coming out of it? It's not coming out of it because the conditions are not met. So let's see what are the conditions there. Work function. This is where more mathematics will start now. Yeah, they will be part of the environment. Yeah, unless you have another plate here which is positively charged and they will come into the plate. Arvind has made a good point. These electrons will be freely in the environment unless you trap them and usually we trap them and make it part of the circuit. So let's understand what is work function. Let's say there is a metal here. Okay, let's say there is an electron here. The color of the electron doesn't mean anything. It's just to understand. Okay, there are 3 electrons in here. Does everybody agree that this electron is easier to take out because it is on the surface? Green is difficult because you have to make sure that the green comes here. It takes some energy to bring it here and then make it free. Blue is very difficult because you have to bring it to the surface and then make it free. Okay, so red is very easy to release, right? So then let's say red needs, I'm just taking some numbers here. Let's say it needs 3 electron volts of energy. If I give 3 electron volts of energy, it is going to become free. Let's say green needs 4 electron volts of energy. And let's say this needs 5 electron volts of energy. Now, what is the minimum energy that I need to make photoelectric effect happen here? It's 3 electron volts. I'm repeating again. The surface electron need the least amount of energy to become free because it's just at the point of it. It already comes out. All it needs is little more push. It's like there is a fence there and somebody can at least jump almost there. He or she needs a little more boost. So this is the minimum amount of energy and this is the work function of this metal. It's a property of the material. This material has work function of 3 electron volts. Is this clear to everybody? Now these are the basic building blocks. It's like we are learning alphabets here. If you don't understand this and you move on, you'll not understand further slides. Okay, clear? Everybody is clear? It is the minimum energy needed. In the example I have given, 3 electron volts is the minimum energy needed. So let's see what happens now. I take a torch, let's say this is a torch, and throw it on this metal. So what happens? I don't know the color of the light. Let's say the color of the light was such that see I can calculate energy of a photon, right? H times frequency. Somehow this calculation gives me 2 electron volts. Let's say the light I'm taking has photons of 2 electron volts. No, this is useless because this photon is not going to be giving enough energy to electron. So no photoelectric effect will happen. You keep doing that all day, nothing happens. Literally nothing happens. Now, some students might argue, what if two of the photons combine together and that gives you 4 electron volts? Now you have enough energy. No, that doesn't happen. Usually that doesn't happen. One electron, one photon. One electron, one photon. No two photons, nothing. So let's see what happens. Nothing happens. Okay. So then I say, okay, let me change the color of the light. I'll take something with more frequency. Let's take green maybe. And let's say this has enough energy of 3 electron volts. अब क्या होगा? This electron, the red electron will become free, take energy, become free, and just become free. Has enough energy to push you through the fence, but then you don't have any energy to run after that maybe. तो यहाँ आके रुक गया कहीं पे, somewhere here, somewhere in the vicinity, stops. ठीक है, it had enough energy to become free, but that is all. It is free now, right? Now this photon cannot release the green and blue photons. This photon has enough energy, which is the work function. Let's say I take another color light, maybe blue light this time. And this has, let's say, 4 electron volts of energy. Let's take an example, 4 electron volts of energy. अब क्या होगा? Let's say, red electron will take 4 electron volts, use 3 electron volts to become free, but then it has a kinetic energy of 1 electron volts. It will keep moving with that kinetic energy. It's like this 11.2. So I don't know how much gravitation you remember now. On the surface of the earth, you take any object and then you throw it with 11.2 kilometers per second, not hour, kilometers per second. It's huge velocity. This is called the escape velocity. The object will reach infinity and stop. Obviously, there is nothing like infinity, but hypothetically, it will reach infinity. This energy was enough to take it to infinity and then it stops. But then no one is stopping you from giving more velocity. If you give more velocity, all that extra energy will make sure that when it reaches infinity, it still is moving with that kinetic energy because energy cannot be destroyed. Same concept here. So red electron has used 3 electron volts to become free, and rest of it is its kinetic energy. Let's look at green. Green says, oh, I can take another photon from this light and I can also become free and stop here. Because it doesn't have any kinetic energy. It becomes free and then stops. Somewhere, not here maybe, somewhere here, it stops. Now the poor blue electron cannot release. The photon doesn't have any energy to release it. Now Arvind, Atri, everybody, I cannot take individual names over and over. Is everything clear so far? If not, I will slow down and explain again. All clear, right? Law of conservation of energy. Energy cannot be created nor destroyed. Yes, Sai Kumar says, would these electrons continue to move with this energy? If this was vacuum, yes. Newton law says if something is moving with 5 meters per second, keeps moving. But in all practical cases, you have air around it, right? So it will collide, stop. Right? So you understand, Sai Kumar, what I'm saying, right? In vacuum, yes. But in reality, it is going to collide with air molecules, convert all of that to heat, and stop. But we'll use this energy to make the current flow in a circuit.